Google DeepMind just dropped something that quietly changes how AI agents actually learn. And honestly, most people completely missed what makes this so important. We're talking about Evo-Memory, a streaming benchmark that exposes the biggest weakness in every LLM agent right now. Plus ReMem, a framework that makes smaller models behave like they have been secretly training themselves at test time. And the numbers are wild because agents using ReMem hit 0.92 success rate and 0.96 progress on AlfWorld with Claude 3.7 Sonnet, almost doubled exact match scores on reasoning benchmarks, and cut step efficiency across the board without retraining a single weight. So let's talk about it. So the thing is, every AI agent you interact with right now is basically storing everything it sees: dialog history, tool traces, API calls, the whole conversation log. But none of them can actually improve their policies at test time from those experiences. They just reply the context window like a tap recorder instead of learning strategies the way humans do. That gap is massive because in real-world environments like interactive problem assistants or embodied agents navigating physical spaces, LLMs are constantly handling continuous task streams, yet they fail to accumulate knowledge from those interactions. They lose valuable contextual insights and the model just forgets what worked and what did. Researchers from University of Illinois Urbana campaign and Google DeepMind recognized this limitation and built Evo-Memory specifically to test whether agents can accumulate and reuse strategies from continuous task streams instead of relying only on static conversational logs. Now here is where it gets interesting. Most current memory systems implement what's called conversational recall. They store dialog history, tool users records, and retrieved documents, then reintegrate that information into future queries. But conversational recall only passively buffers information. It doesn't actively modify the agent's processing strategies for related tasks. It's like reading your notes before an exam but never actually studying the material. Evo-Memory flips that completely by introducing what they call test time evaluation, where LLMs retrieve, integrate, and update memory continuously during deployment. And the framework formalizes this as a tuple FURC, where F is the base model, U writes new experiences and evolves the memory after each step, R is the retrieval module, and C handles context construction. That U component is the breakthrough here because it's the piece that turns memory from a passive buffer into an active learning system. The benchmark itself restructures conversational datasets into sequential task streams. Instead of isolated prompts, each dataset becomes an ordered sequence of tasks where early items carry strategies that are useful for later ones. And the suite covers AIME 24, AIME 25, GPQA Diamond, MMLU Pro across economics, engineering, and philosophy, ToolBench for tool use, and multi-turn environments from agent board including AlfWorld, Baby AI, Science World, Verico, and PDDL planning. And evaluation happens along 4 axes. Single turn tasks use exact match or answer accuracy. Embodied environments report success rate and progress rate. Step efficiency measures average steps per successful task. And sequence robustness tests whether performance stays stable when task order changes. That last one is critical because if your memory system only works when tasks arrive in a specific order, it's not really learning. It's just overfighting to the sequence. To set a baseline, the research team defined XPRAG. Each instruction becomes a structured experience text with a template that includes the input, the model output, and a feedback like a correctness signal. In new tasks, agents retrieve similar experiences and combine them with the current input. XPRAG already shows clear gains, hitting an average exact match of 0.60 across Gemini 2.5 Flash on single turn benchmark. But the real breakthrough is ReMem. And this is where the performance numbers get crazy. ReMem introduces what they call an action think memory refine pipeline. It's a control loop that tightly integrates reasoning, task actions, and memory updates for continual improvement. The system has 3 core modules. Think handles reasoning and decomposition. Refine memory retrieves, prunes, and organizes the memory store, and Act executes the action in the environment. Those 3 modules interact with the environment and the learned memory in a continuous loop, meaning the agent iteratively searches, synthesizes, and evolves its memory across multiple tasks. It's not just retrieving past experiences, it's actively reflecting on them, deciding what to keep, what to prune, and how to recognize the knowledge base dynamically during reasoning. This makes memory an explicit object that can be dynamically edited during reasoning, which is exactly the kind of meta-learning capability the field has been predicting for years. The numbers back this up across the board. For Gemini 2.5 Flash, ReMem reaches an average exact match of 0.65 across AIME 24, AIME 25, GPQA Diamond, and MMLU Pro subsets. That's a 5-point jump over XBRAG. On ToolBench, it hits 0.85 API call accuracy and 0.71 task accuracy. But the impact is even larger in multi-turn environments, which is where memory systems are supposed to shine. On Claude 3.7 Sonnet, ReMem reaches 0.92 success and 0.96 progress on AlfWorld, 0.73 success and 0.83 progress on Baby AI, 0.83 success and 0.95 progress on PDDL, and 0.62 success and 0.89 progress on Science World. That gives an average of 0.78 success and 0.91 progress across datasets. On Gemini 2.5 Flash, ReMem achieves average 0.50 success and 0.64 progress, improving over history and React style baseline in all 4 environments. And step efficiency is also improved, meaning agents complete tasks with fewer steps, which is a huge deal for real-world deployment where every API call costs money. And honestly, the community response to this was immediate. The research team compared more than 10 representative memory modules under a single framework. They tested retrieval-based systems, workflow memory, hierarchical memory systems, dynamic cheat sheet variants, agent workflow memory, and systems like Mem0, Zeb, and LangMail. They excluded systems like Memory GPT and Memory Bank that only target factual recall because Evo-Memory is designed to test evaluating and procedural memory. The goal isn't to improve the underlying LLMs themselves, it's to isolate the effect of search and evaluation in memory mechanisms. And ReMem consistently outperforms more complex designs, which tells you that simplicity pulls tight integration-based architectural complexity every time. Now, the crazy part is how ReMem's performance correlates with task similarity. Using encodings from the retriever encoder, the research team computed average distance from tasks to their cluster center. ReMem's margin over a history baseline correlates strongly with the similarity measure, with reported Pearson correlation about 0.72 on Gemini 2.5 Flash and 0.56 on Claude 3.7 Sonnet. Structured domains such as PDDL and AlfWorld show larger improvements than diverse sets like AIME 25 or GPQA Diamond. That means ReMem works best when tasks share underlying structure, which makes sense because the memory system can abstract reusable strategies rather than memorizing surface-level patterns. In fairness, there are still limitations. ReMem improves exact match, success, and progress without retraining base weights, but it doesn't handle messy or unlabeled datasets well, and it can't adjust mid-experiment. Once it starts a run, it goes all in. The system also struggles with raw images or files larger than about 5 GB. The bigger limitation isn't computing power though, it's judgment. Teaching ReMem how to recognize which ideas are meaningful, not just statically correct, is the next frontier, and certain methods like MemOS and LangMem aren't fully compatible with embodied environments, so they were excluded from multi-turn datasets. But here is what makes this research so important. Evo-Memory forces models to operate on sequential task streams instead of isolated prompts. It compares more than 10 memory architectures under a single framework. Simple methods like XBRAG already show clear gains. ReMem's action think refine memory loop improves exact match, success, and progress without retraining base weights. And this makes test and evaluation a concrete design target for LLM agent systems, which is exactly where the field needs to go. Because right now, most agents are just glorified chatbots with better retrieval. They don't evolve, they don't learn from mistakes, they don't transfer strategies across tasks. ReMem changes the dynamic completely, and the timing of this release matters because memory is becoming the bottleneck of agent performance across the industry. Simply enlarging LLM context windows only delays the problem. Models get slower, costlier, and still overlook critical details. Mem0, which recently dropped its own scalable memory architecture, reported a 26% higher response accuracy compared to OpenAI's memory feature on the Locomo benchmark, 66.9% versus 52.9%. They also slashed P95 latency by 91%, 1.44 seconds versus 17.12 seconds, by operating over concise memory facts instead of reprocessing entire chat histories. That's a 90% reduction in token consumption, requiring only around 1.8k tokens per conversation compared to 26k for full context methods. So the industry is converging on the same insight. Persistent, structured memory-based brute force context length every time. What also stands out is how Evo-Memory positions itself against existing benchmarks. Locomo focused on very long-term conversations, each encompassing 300 turns and 9k tokens on average over up to 35 sessions. LongMem Evolve tested memory agents but used synthetic conversations with limited topical diversity. Real Talk and Storybuild offered multi-turn evaluations, but none of them provided comprehensive coverage of the four core memory competencies that Evo-Memory targets: accurate retrieval, test-time learning, long-range understanding, and selective forgetting. By transforming existing long-context datasets and incorporating newly constructed datasets into a multi-turn format, Evo-Memory effectively simulates the incremental information processing characteristic of memory agents. That's the key innovation. It's not just about storing more tokens. It's about learning better strategies from accumulated experience. The broader picture here is that we're entering the stage where AI doesn't just assist the process, it is the process. And memory is the foundation of that shape. When Future House released Cosmos, an AI scientist that works 12 hours straight and makes real discoveries, one of its core capabilities was managing accumulated knowledge across hundreds of similar AI agents sharing a single internal memory called a world model. When Google introduced DStar, an AI data scientist that writes, tests, and fixes its own Python code, the system runs multiple specialized agents with shared memory to iterate up to 20 times per task. And when China's Moonshot AI unveiled GPQA thinking, they highlighted its ability to execute up to 300 sequential tool calls without human input, chaining hundreds of reasoning steps through accumulated context. All of these systems rely on memory that evolves, not memory that just stores. That's where we will wrap it up. One thing I'm curious about now is how this framework influences the design of future agent systems, especially as companies start building agents that run for days or weeks on complex tasks. Will we see ReMem-style memory loops become standard in every agent architecture, or will there be a new wave of memory designs that go even deeper into procedural knowledge and skill transfer? Drop your thoughts below. Make sure you are subscribed, hit that like button, and I will see you in the next one.